Hey everyone, welcome back. In today's video, we are going to tackle some key questions on linear algebra. We will cover important topics like vector space, vector subspaces, and dimension of vector subspaces. If you find this video helpful, don't forget to give it a thumbs up, subscribe to the channel, and share it with others who might benefit. Alright, let's dive in. So, here is question LA13 on your screen. So I would recommend to pause the video and solve this question by your own. So the question says that let let V is a vector space of all the function f mapping from R to R. Then which of the following is not a subspace of V? So the first important thing we need to see is it is asking for not. Okay, so we need to check which of them is not a subspace of V. So V is a vector space of all functions f which are mapping from R to R. Basically, real valued function which has real value input and real value output. Okay. So, for example, V will contain functions like x, x square plus 1, sine x, etc., etc. Because all these functions are from R to R, right? So the space of all such function is V. So it's a pretty huge vector space which contains all the function mapping from R to R. All right. Now we will go one by one. We will check all the three options, which of them is a vector space or not, vector subspace or not. So the first option, A, it says that W1 is a subspace such that the function f which are in W1 belongs to V such that function f is bounded. All right. So basically, W1 is a subspace of all bounded functions mapping from R to R. So we can say that uh, W1 is a subspace of all functions which are bounded and R to R, that is mapping from R to R. So is it a subspace? So you know that to prove it a subspace, we need to prove uh, two things, right? The first one is it should contain the null vector, basically in this case the null function, and this is this null function, that is zero function, will be contained in all the subspaces. Okay, so that is very trivial, so there is no need to check that. The second thing we need to check is that if vector v and w belong to the subspace v, then their linear combination, that is alpha times v plus beta times w, should also belong. If v and w belongs to the subspace w, then their linear combination alpha v plus beta w should also belong to the subspace w. That is this closure property should be satisfied. So the first one is trivial. All these subspaces will contain the zero function, right? So it's pretty trivial because zero function is bounded, it is continuous, it is monotonous. I mean, it's a trivial thing, so no need to check. All we need to check is this second property in all the three options. That is, if V and W are belonging to subspace, then their linear combination also belong. So yeah, for bounded function, this is true. A linear combination of two bounded function is also bounded, right? So hence we can say that closure property is satisfied in case of bounded function. So W1 is a subspace of V. Okay, so we can see this by an example. We can see this by an example. For example, I have this bounded function sin x. This is bounded function, right? Because sin x belong to the range -1 to 1. So it's a bounded function. You need to check y-axis, not x-axis, right? Because we need to check the output. So you can see the output is bounded from -1 to 1. And we take another function cos x. Okay, so sin x is f1, cos x is f2. So both are bounded, and we will take a linear combination of the both the function, that is sin x plus cos x. And you see that this is also bounded, the pink one. right? The blue one is the first function sin x, the orange one is the second function cos x, and the pink one is their linear combination. So the linear combination, this is also bounded. So we can say that this W1 is a subspace because if two functions f1 and f2 belong to the subspace W1, then their linear combination alpha time f1 plus alpha time f2 also belong to the subspace W1. Okay. Now we will check second option. Second option is saying that subspace subspace W2 is all function f sorry belonging to V such that f is continuous. F is continuous. Okay. So again we need to prove this linear combination property. Uh, So we know that linear combination of two continuous functions is also continuous, right? So for example, if two continuous functions f1 and f2 belongs to w2, then their linear combination alpha times f1 plus beta times f2 also belong to the subspace w2. So these are trivial thing because if you take a linear combination of any two continuous function, it will be continuous only, right? Because you are just for example, this is one function, right? If you if this function f1 is continuous, right, then alpha times f1 is also continuous because you're just scaling the function. Same goes for example, if you take this another function f2, then beta times f2 is also continuous because f2 is continuous, so you just scale that function and it is also continuous. And because these two continuous, this alpha times f1 and beta times f2 is continuous at every point x, right? At every point this is continuous, at every point this is continuous. So their linear combination will be also continuous at every single point. Okay, so we can say that W2 is a subspace of V because it holds the closure property. And we can see this using an example also. For example, I take this function x. This is continuous. I take this another function sin x. This is also continuous. And their linear combination x plus sin x, this green line, this green curve is also continuous. See, this is also continuous. So linear combination of two continuous function is also continuous. So this closure property satisfied. So it's a subspace. Now we will see the third one. The third subspace is given W3 is all functions f belonging to the vector space V such that f is monotonic. Monotonic. That is, it's a monotonic function. Now there is a catch here. It is not given that whether this subspace W3 contains monotonically increasing or monotonically decreasing function, right? It is just they are just saying that f is monotonic. So it can contain a function which is monotonically increasing, and it can also contain a function which is monotonically decreasing. So both this function f1 and f2, this f1 also belong to W3, that is a monotonically increasing function, and this f2 also belong to W3, that is monotonically decreasing function. So W3 contains both monotonically increasing and decreasing function. So we know that linear combination of two monotonically increasing function is also monotonically increasing. Linear combination of two monotonically decreasing function is also monotonically decreasing. But linear combination of monotonically increasing and a monotonically decreasing function is not monotonic. That is, linear combination of monotonic increasing and monotonic decreasing function is not monotonic. All right. So for example, if we have a function f1 equal to e to the power x, this is monotonically increasing function. Okay. This is an increasing function. All right. It is a monotonically increasing function. If we take f2 is equal to e to the power minus x, then this is monotonically decreasing function. All right. And if we take the linear combination, if we take the linear combination f1 plus f2, that is e to the power x plus e to the power minus x, then this is neither increasing nor decreasing. This is neither increasing nor decreasing. Okay, so we can see this here. This is e to the power x. This is monotonically increasing function, right? This is monotonically increasing function. This one is e to the power x minus x, the white curve. This is monotonically decreasing function. We take the linear combination of both, we get this blue one. See, this blue one is e to the power x plus e to the power minus x, and this is neither monotonically increasing nor monotonically decreasing function. So, W3 is therefore W3 is not a subspace, not a subspace. Why? Because F1 because F1 and F2 belongs to W3, but F1 plus F2 doesn't belong to W3, right? So F1 and F2 belong to W3, but their linear combination doesn't belong to W3. So that closure property is not satisfied. So therefore, W3 is not a subspace. So W3 is not a subspace. Let's see question LA14. So it is saying that let A be an M cross N matrix. So uh, uh, A is an M cross N matrix and B is an N cross M matrix, and we are given that N is less than M. Okay. Then we need to check this thing. So it is asking for AB is invertible or not. So because AB is nothing but a matrix, right? The multiplication of two matrices is a matrix itself. So a matrix is invertible if and only if it is full rank, right? So first of all, what is AB? AB is nothing but you multiply A and B, you will get M cross M. So AB is invertible, invertible if and only if it is full rank matrix, full rank matrix, right? That is the rank of AB should be M, right? And what is rank? Rank is nothing but the dimension of the column space, that is the number of linearly independent column vectors. Okay, so basically we need to check the rank of AB. So what is rank? Rank is dimension of column space, right? And it is also equal to the dimension of row space, right? And what is the dimension of column space? This is nothing but number of linearly independent column vectors, and this is nothing but number of linearly independent row vectors, right? But because here the matrix A is not square, so the rank should be less than equal to minimum of n comma n comma m. Why? Because if you see this the column space of A, if you see the matrix A, how many column vectors we have? We have n column vectors, right? We have n column vectors. So if we have n column vectors, then number of linearly independent column vectors cannot be more than n. It should be less than or equal to n. Similarly, if you see this, because the row space and column space has the same number of dimension, how many row vectors we have? We have m row vectors. So in case of A, number of column vectors, because A is m cross n, number of column vector is n, and number of row vector is m, right? So if the number of column vector is n, then the number of linearly independent column vector would be less than equal to n. It cannot be more than n, and the number of linearly independent row vectors should be less than equal to m. Okay, so the rank should be less than equal to minimum of these two. The rank should be less than equal to minimum of these two. Okay, and we already know that rank of A, which is an M cross N matrix, should be less than equal to N. and rank of B, which is an n cross m matrix, should be less than equal to n. Why? Because it is given that n is less than m, right? It is given in the question that n is less than m. We know that rank of A, which is an m cross n matrix, it is nothing but a linear number of linearly independent column vectors, and we have n column vectors. But because n is less than m, so it cannot be m. It should be less than equal to n, right? So these things are given. Now there is one property that rank of a matrix AB, rank of a matrix AB should be less than equal to minimum of rank of A comma rank of B. So this is an important property. Okay, this is an important property. So take a note of it. That rank of a matrix AB should be less than equal to minimum of rank of A and rank of B. Now rank of AB less than equal to minimum. What is rank of A? Rank of A should be less than equal to n. So let us suppose we take the maximum of it, n, and rank of B should be less than equal to n. We take maximum of it, n. So it should be less than equal to n comma n. That is, it should be less than n, because minimum of n and n is n itself. It is less than n, and we already know that n is less than m. So if n is less than m, then rank of AB is less than equal to n. So rank of AB should also be less than m, because m is greater than n, right? Because m is greater than n. This is given in the question. So if rank of AB is less than equal to n and n is less than m, then rank of AB should be less than m, right? Therefore rank of AB is less than m, right? It is less than m. And I already told you that AB is invertible if and only if it is a full rank matrix, right? AB is invertible if and only if it is a full rank matrix. That is, rank of AB should be m, but here rank of AB is less than m. Therefore AB is not invertible. AB is not invertible. That is option A. So and here it is given that n is less than m. So rank of A, which is an m cross n matrix, should be less than equal to n. It cannot be m. It's not possible to be m, because m is greater than n, and n is the total number of column vectors. So if total number of column vectors are n, then total number of linearly independent column vectors cannot be more than n. It should be less than equal to n, right? So this is how we solve this question. Okay. If you like this video, then do subscribe my channel, share with others. uh, Till then, bye. Thank you.